Okay, thanks everyone for joining us for the 2DCC webinar today. We have Dr. Leo Lee from Brown University. And Dr. Lee, you are good to get started.
Okay, thanks for the introduction, and also thanks for the invitation. This is my third time visiting Penn State in the last 3 years, albeit it's virtual. So today I want to talk about something different and more recent that we have been working on. It's angle resolved transport nonreciprocity and spontaneous symmetry breaking in multilayer graphene. So I'll explain what this means, and please feel free to interrupt me if you have questions. Right. So a brief outline of the talk is as the following. First, I'll quickly discuss Coulomb interaction of flat energy band and some brief history of spontaneous symmetry breaking in such a system, right, when Coulomb interaction dominates. And most of the talk will be focused on angle resolved transport measurement and how that can be used to reduce rotational symmetry. And lastly, the most important part is angle resolved non-reciprocity, which I'll explain what that means. And using this tool, we're able to probe broken rotational and transversal symmetries. So flat energy band, the system that we're going to focus on is multilayer graphene. There has been a lot of development in the last several years. Multilayer graphene mostly fall into two big categories. One of them is taking graphene crystals, different type of graphene crystals, and introduce a twist. Right. Theoretically, this system is predicted more than 10 years ago, and the prediction is that as you introduce a rotational misalignment, a Moiré superlattice will emerge, and the periodicity or the lattice constant of the superlattice is controllable using the twist angle. And in the case of two monolayer graphene, at around 1.5 degree angle, which is also called the magic angle, the band becomes really flat, and it's also isolated from the remote band, right? And that creates an ideal situation to study the influence of Coulomb correlation in a flat energy band. And there's a different type of approach that's discovered a little more recently, that you can take natural formed multilayer graphene crystals, such as a banal bilayer graphene, where the B sublattice of one layer is stacked directly on top of the A sublattice of the other layer, right? Extremely simple crystal form. In such material, you just need to apply a perpendicular electric field, or we call displacement field, which breaks the inversion symmetry, opens up a gap at the charge-to-charge point, right? As you apply a large enough D, the edge of the band becomes flat enough that Coulomb interactions start to dominate, right? So the interest of this talk is to look at the influence of strong Coulomb correlation in this scenario, right? When you have a flat energy band in multilayer graphene, Coulomb interaction dominates, and some interesting quantum phenomenon comes out. Some of the phenomenon is quite well studied, that we think we have a pretty good handle on it, right? For example, isospin symmetry breaking. The isospin symmetry breaking can be probed using many different methods. What I'm going to show here is the transport response, right? This is measure longitudinal resistance as a function of Moiré band filling, measure at B equals 0 in the twisted trilayer graphene. I showed the reference down here, right? And at integer filling of 1, 2, 3, that means there's 1, 2, 3 electron per Moiré superlattice. Because the degeneracy is 4, at these fractional filling, we expect metallic states, but something exotic is happening that shows up as the peaks in the resistance, right? Showing that there's some Coulomb-driven phenomenon. And at the same time, if we were to measure hole density, right, the number of free electrons in the system, it resets at almost all integer filling. So this kind of behavior can be, first of all, the degeneracy is 4, right? Because that, one, there's spin degeneracy, and two, in multilayer graphene, Fermi surfaces are located near the corner of the Brillouin zone, right? And these three blue corners are inequivalent to the yellow corner. They're connected by twofold rotation and time-reversal symmetry. So it behaves as some kind of an isospin, right? And spin and valley together adds up to fourfold degeneracy. And the symmetry breaking here can be easily understood by considering a fairly cartoonic picture, right? Within the, when you put electron in a Mori superlattice, electrons tend to go on these islands where the A sublattice of one layer overlap with A sublattice of the other layer, right? So when you put a little bit of electron in there, electron are isospin unpolarized, meaning that they randomly pick a isospin flavor, right? That's what the 4 bands are showing, that there are 4 isospin flavor. But when you get to integer number of electron per island, right, the exchange interactions start to play a dominating role, which is driven by the strong Coulomb correlation. And what happens is that when you get to these integer filling, one of the flavor just becomes energetically favorable, or the system starts to polarize into one isospin flavor, right? And as you can see, that it opens up an energy gap, and that gap is why we have a resistance peak, and also why the number of free electron diminish to 0, right, when a gap forms. And this cascade of Fermi surface reconstruction, right, these process is also directly seen if you measure chemical potential in the system, right? The top panel is showing chemical potential as a function of Mori band filling. At every integer filling, the potential goes down and up. It goes down because of this band, one band gets separated out, right? So this is a fairly well understood phenomenon that Coulomb interaction will drive spontaneous breaking of isospin symmetry, right? Lift the isospin degeneracy. There are different types of Coulomb-driven phenomena. Some are more exotic and less understood. For example, the zero-field superconducting diode effect. I believe I talked about that last time, right? So in some of the graphene Mori structure, the superconducting transport behavior is highly non-reciprocal, meaning the critical current is highly dependent on the direction of the current flow, right? And that gives rise to this diode effect, where we can control, we can tune between normal state and superconducting behavior just by controlling the direction of the current flow. Without going into too much details, there are theoretical proposals that suggest that this is really just coming from coexistence of superconductivity and a valley imbalance Fermi surface, right? The symmetry there, you just need to break inversion and time reversal, and which naturally arises when you have valley polarization that could give you this kind of phenomenon. So I already spent one seminar on this. Let's don't get to too much detail here. And the Coulomb interaction within the flat band could have other interesting phenomena, which will be more related to the topic here. For example, one of the very interesting consequences of strong Coulomb correlation had to do with the rotational symmetry breaking, right? You can start with the Fermi surface that's circular, so it preserves rotational symmetry. And when you introduce very strong Coulomb interaction, it could spontaneously undergo it's called a quadruple distortion, right? The Fermi surface becomes peanut-like. It breaks rotational symmetry, and there are 2 principal axes, right? X and Y. Each of them are a mirror axis. So twofold rotational symmetry is preserved, but everything else is broken, right? The resulting phase is often referred to as orthorhombic anisotropy, and this phenomenon has been studied in a wide range of materials, and it's related to the topic of electronic pneumaticity, right? People want to study what is the origin of this, how does Coulomb interaction give rise to this spontaneous rotational symmetry breaking, and more importantly, what is the relationship of this with other emerging phenomena such as superconductivity, right? So here's one of the reference that's quite relevant to this work, right? If you have spontaneous rotational symmetry breaking in a semi-2D system, you can directly probe this using angle resolved transport measurement. And in this work, the material that's being studied is some kind of cuprate material, right? Copper oxide. And the device geometry is shown here. It's called a sunbeam geometry. What happened here is that you have a center contact, this big orange circle is a piece of gold, and all the blue are the sample, right? So every piece of these small sample has a whole bar shape. So essentially, this device allow you to flow current. You start from a single crystal, right? And you pattern them into these, I think there's 36 of these whole bar samples. It will allow you to flow current in this material in many different directions. With each current direction, you can measure longitudinal resistance and transverse resistance, right? And you see some kind of angular dependent oscillation, both in transverse resistance, the top panel, and the longitudinal resistance, right? And they both have a period of pi, and but interestingly, the two channel has a phase shift that's about 45 degrees, which obviously is very important, right? And this kind of angular dependence can actually be understood very straightforwardly by considering the symmetry analysis of underlying electronic order, right? For example, if we have a orthorhombic anisotropy that look like this, meaning that there are two mirror axes, X and Y, right? When you flow current along any mirror axis, transverse resistance has to go to 0, right? Because of definition of a mirror axis. And longitudinal resistance had to be either maximized or minimized. In other words, transverse response is asymmetric around mirror axis, and longitudinal response is symmetric around mirror axis, right? So that essentially gives us all the constraint. What I'm plotting here is a quick schematic to show what I'm talking about. The green solid line at the top highlights the direction of the mirror axis, right? And along each mirror axis direction, longitudinal resistance is either maximum or minimum, and transverse resistance is 0. So that naturally accounts for the pi periodicity, because there are two mirror axes. It also accounts for the phase shift of pi over 4 between the longitudinal and transverse channel, right? So a lot of the data I'm showing, I will also, right? So it's captured by a equation like this, right? And we can also plot the same data in a polar plot, right? So in a polar plot, a longitudinal is always positive, and the transverse changes sign. So to make it possible, we just plot absolute value and just color the positive red and the negative blue, right? But most importantly, there's a phase shift of pi over 4 between the two channels. Okay, and I should mention that a longitudinal channel has a offset because the sample has a intrinsic conductivity, right? It's not 0. And transverse channel in this data I'm showing doesn't have an offset, so RH should be 0. RH should be 0 as long as there's no Hall conductivity at B equals 0, right? As long as there's no anomalous Hall, RH should be 0. So another way of saying this is that if there's an anomalous Hall effect, right, we do expect the transverse channel has to shift in one direction, right? So this actually become a fairly interesting probe. So we do want to do angle resolved measurement in multilayer graphene. Of course, we don't have the real estate to build a sound beam sample, right? Sound beam geometry has a characteristic length scale of 3 millimeter by 3 millimeter. And the sample we're dealing with has a length scale of 10 micron by 10 micron. So to work around this, we patterned the very small multilayer graphene crystal into a sunflower-shaped sample that has a circular channel and 8 contacts, 8 petals, right? And it does allow us to flow current in different directions, and along each direction of current flow, right, we can measure longitudinal response like this and transverse response like that, right? And from 0 to 2 pi, we have angular resolution of about 20 degrees in the setup, right? And so longitudinal, if we use a small DC current bias, right, we get a longitudinal resistance and transverse resistance defined like this, right? And the angular dependence is shown here. These are actual data, I think, measured from both banal bilayer graphene. This is from twistor trilayer graphene, so nu equals 2, right? And the behavior, the black solid line is the equation I just showed you, the expected behavior for orthorhombic anisotropy, and the mirror axis is these two dashed lines, right? Along the direction of mirror axis, transverse resistance go to 0. Okay, so before moving further, I do want to mention, even though this looks like we have an angular resolution that's about 20 degrees, the actual sample can overcome this. Our actual ability is not limited by this angular resolution. The reason for that is if you have a sample, a circular sample like that, you apply a source and apply a drain at some point, right? The electric potential distribution across the sample is fully determined by the location of source and drain and the conductivity matrix, right? For example, if you have an isotropic conductivity matrix, this will be the potential distribution, whereas if you turn on an anisotropy, right, with the principal axis that's marked by these two black arrows, along the long arrow direction, that's where the conductivity is high, right? The distribution across the entire sample will just change accordingly, right? Similarly, if you change the location of source drain, and you can calculate the distribution according to the conductivity matrix. And what this means is that the 8 contact actually allow us 420 independent measurement configuration, right? You choose any 2 leads as source and drain. You can measure voltage response between any other leads. And all of these data are fully deterministic by a conductivity matrix. So we can take all of them and just fit what the conductivity matrix is. This is not limited by any angular resolution, right? So for example, I'm plotting, this is really limited by how big the slide is. There are 420 points. I'm plotting some of them. And the dashed line is a predicted value from one conductivity matrix. The shade is the expected error bar. The reason there's an error bar is because the contact is not a point, right? It has a width. So we can use this model, we can calculate, for example, if you have a contact here, you'll have a very small error bar because there's no voltage drop. But if you have a contact here, you will have a bigger error bar because there's a lot of voltage drop, right? So you can see that most of these match very well. The points that deviates slightly is very strange measurement configuration, right? You're just measuring a corner of the sample. And even that, most of the data falls within the expected error bar, right? So, so we can directly extract the conductivity matrix. We also get a very good sense of how uniform the sample is. Okay, so that's kind of the basis of our method. We can also go beyond the orthorhombic anisotropy, right? Orthorhombic anisotropy is really a unique type of rotational symmetry breaking. It has 2 mirror axes. It breaks rotational symmetry, but preserve twofold rotation. You could easily come up with other type of rotational symmetry breaking, right? For this, in this case, the circular Fermi surface shift in one direction, right? So that the system gains a non-zero momentum, but that there's only one mirror axis, right? The fact that you break twofold rotational symmetry means that the perpendicular orthogonal mirror axis will have to disappear. You can also have something like this. It preserves threefold rotational symmetry, but breaks twofold rotational symmetry, right? And to be more complete, to be sensitive to, let me clarify. If you were to measure a linear transport response, right, you shouldn't be able to tell the difference between 1 and 2, right? When you have something that has one mirror axis, when you measure linear transport response, you just measure the same thing as a orthorhombic anisotropy. And in the third case, you should measure something that's isotropic, right? We need something that's more sensitive to this type of symmetry breaking where twofold rotation or inversion is broken. And it turns out the key is to look at a line cut along the energy dispersion, right? If you have orthorhombic anisotropy, any direction you take a line cut, the energy dispersion is symmetric, right? Positive, negative momentum is the same. Whereas if you break twofold rotation or inversion symmetry, in when you have this situation, the transport response is supposed to be reciprocal, meaning positive and negative current give you the same thing, right? But in the second case, if you do the line cut along the mirror axis, right, the dispersion should be highly asymmetric, and as a consequence, the transport response should be non-reciprocal, right? So we should be able to detect this kind of a unique angular rotational symmetry breaking, and to go further, we should be able to tell the difference between the one-fold symmetric and three-fold symmetric situation just by doing the angular dependence of a non-reciprocal transport measurement, right? Because in the perpendicular direction, in this case, right, we actually expect non-reciprocity to go to 0, right? So the angular dependence in this case should be one-fold symmetric, and in this case to be three-fold symmetric. Okay, so we define non-reciprocity as the difference in the voltage response between current flowing in phi and the phi plus pi, right? So forward and reverse bias direction. And there should also be a transverse response, right? Which is just defined by the forward and reverse bias difference in the transverse channel. And the angular dependence is actually fairly straightforward to understand by considering the symmetry constraint, right? So for the first case, because there's only one mirror axis, the angular dependence should have a periodicity of 2 pi. And the longitudinal and transverse channel should have a phase shift of pi over 2. Just because along the mirror axis, the transverse response should go to 0, right? And if the system has 3 mirror axes, right, then both longitudinal and transverse channels should have a period of 2 pi over 3 with a phase shift of pi over 6, right? That's just the symmetry constraint. And moreover, transport non-reciprocity, right, can be measured more straightforwardly using second harmonic nonlinear response. To show why that's the case, here I'm plotting the IV curve of, this is from twisted trilayer graphene, although this is very universal, right? The dashed black line is the linear response. It's just a linear fit to the small current response. And as you go to slightly larger current, you can see that it's deviating from the linear response. So there's some kind of a nonlinear component. If you subtract the linear response, you can see the nonlinear component, that's a non-reciprocal component, right? Has a quadratic dependence in current. This is a DC current measurement. So in this case, if you were to apply a AC current with the sine omega t frequency, right, the nonlinear response or the non-reciprocal component should be sine square omega t, right, which is proportional to cosine 2 omega t. So you should be able to measure the non-reciprocal component just by looking at the second harmonic frequency of AC current bias, right? And that's what we did here. And there are two things. One, as a function of AC bias, it's quadratic, right, because of this quadratic term. And two, when you rotate the measurement geometry by 180 degrees, even though the sample respect the twofold rotational symmetry, we see a very clear sign reversal, which shows that when you have non-reciprocity, twofold rotational symmetry is broken, right? That's also consistent. And right. So now we can just look at the measurement data of the non-reciprocity as a function of angle, right? I'm just going to show a few typical response to convince you that, to give you a sense of what angular dependence look like. In this particular example, this is measured from Bernal bilayer graphene at this point of the phase space, right, at b equals 0. And both longitudinal and transverse channel are one-fold symmetric, meaning with a period of 2 pi. And the phase shift between longitudinal and transverse are pi over 2, right? So they can be expressed by this equation, right? V1 is the amplitude, and the beta here is the direction of the mirror axis, right? And the phase shift is naturally captured by the cosine and sine function, right? Because transverse channel is asymmetrical along the mirror axis, and the longitudinal response is symmetric around the mirror plane. Okay, so that's consistent with the one mirror axis. And as some other points, we do observe situation where the angular dependence is mostly threefold symmetric with a period of 2 pi over 3, right? And most importantly, the phase shift between the longitudinal and transverse channel are pi over 6, right? And that can be captured by this equation where the threefold symmetry is this 3 in front of 5. Okay, I should mention that because in this measurement, the quality of the fit or the quality of the angular oscillation is limited by a little bit by angular resolution for the threefold symmetric case, right? But most of the situation, we have something that's slightly different. It's not one-fold symmetric. It's also not completely threefold symmetric, right? So, for example, something like this. What happens here is that we have a linear combination of one-fold plus three-fold. The angular dependence of the two channel seem a little chaotic, but I'll show you that this actually is completely within our expectation. That if we were to plot the one-fold component and three-fold component separately, right? In both channels, it's a one-fold plus three-fold. But if you look carefully, the one-fold component between the two channels has a phase shift of pi over 2, and the three-fold component has a phase shift of pi over 6, right? So consequently, in the longitudinal channel, the one-fold and three-fold component are out of phase. That's why you see something that look like two prominent positive peak, and the third one disappeared because it's out of phase. But in the transverse channel, these two are in phase, because the one-fold and three-fold component have different offset, right? And so in the transfer channel, you have one prominent peak and the other two are suppressed. And vice versa, a lot of it look like this, right? And in the longitudinal channel, the one-fold and three-fold component are in phase, and in the transfer channel, it's out of phase, right? So to sum up, that all of the angular dependence can be universally expressed by this one simple equation. There are two amplitude terms, the one-fold amplitude and the three-fold amplitude, but there's only one mirror axis or mirror plane direction, right? And I should mention that for all of these, two-fold rotation or inversion is broken, right? Even for the three-fold symmetric term, there's no two-fold rotational symmetry. And as long as you have a non-zero V1, three-fold rotational symmetry is broken, and there's only one mirror axis, right? So in the polar plot, I'm marking the mirror axis orientation using the green solid line. Okay, great. So we see this angular dependence that seems fairly systematic, right? And the most important question is what's giving rise to this, right? And the clue we have is that that two-fold rotational symmetry or inversion symmetry is always broken when you have a non-zero, non-reciprocal response. And to have two-fold rotational symmetry or inversion symmetry breaking and see a non-reciprocal response, there are generally two big scenarios. One is that inversion is broken or two-fold is broken and time reversal is preserved, right? This involves some kind of a scattering mechanism combined with band topology, for example, barrier curvature dipole. There's already a lot of discussion that talk about this phenomenon. And in the following, I will show that I don't think this explains what we have, but I'll get back to that. But for now, there's another scenario where C2 and T are both broken, right? So not only do we break rotational symmetry, we also break time reversal symmetry. The reason that this comes up is because in multilayer graphene, there's always trigonal warping. When you combine trigonal warping with valley polarization, right, C2 and T are simultaneously broken, and that can naturally account for the origin here. And I give you several examples, schematic of valley polarization, right? When you have trigonal warping at low density, usually each valley you have 3 Fermi pockets. If you only occupy Fermi pocket in one valley, or if you only occupy one trigonal shape Fermi surface in one valley, right? C2 and T are both broken. But at the same time, you could have just a slight imbalance, meaning that one valley, charge carrier in one valley slightly more than the other valley, right? That also satisfies the symmetry constraint. So while valley polarization itself is difficult to probe, we do have this opportunity that in some of these materials, we have orbital ferromagnetism that essentially comes from valley polarization. For example, in this twisted trilayer sample, we have orbital ferromagnetic order near integer filling, right? And that provides an opportunity for us to look at the origin of the non-reciprocal response. The challenge here, there is a bit of challenge that in twisted trilayer graphene, apart from this very flat Moiré band, that's the red line, right? This is a calculation. There's also a Dirac cone that coexists with the flat band. While the flat band gets gapped out and develop all these, let's say, orbital ferromagnetic order, the Dirac cone is always gapless, which means that the sample always is somewhat metallic or conductive, right? As a result, when you have the orbital magnetic order, you try to measure the magnetic hysteresis, right? At least in the Hall channel, there's a very big slope that somehow makes this loop look somewhat small, right? Although you can see that there definitely is a magnetic hysteresis loop. Fortunately, we can also control the magnetic order using a DC current, right? The DC current also coupled to the valley polarization, and that creates this hysteresis that's looks a lot better defined. And so this is measured from twisted trilayer graphene. And the size of this loop, right, essentially tell us how strong is the valley polarization order, right? When this hysteretic switch happens, that's essentially when you go from one valley polarization to the opposite valley polarization. And so if we measure this as function of temperature, right, you can clearly see at about 2.523 Kelvin is when valley polarization start to onset with lowering temperature or start to vanish with increasing temperature, right? So what we can do is we compare the temperature dependence between the size of the hysteresis loop, right? This tells us that valley polarization start to onset about 2 to 3 Kelvin. Compare that with the angular dependence. V1, V3 are the amplitude of the angular oscillation, and they seem to be some good agreement, meaning that we only see non-reciprocity when we have valley polarization, and when valley polarization goes away, non-reciprocity also goes away, right? There seems to be a very nice scaling factor here, but you tell us something, but this is fairly detailed that we don't have to get into for the time being. Okay, so if valley polarization accounts for the twofold rotational or inversion symmetry breaking, as well as the time reversal symmetry breaking, right? There's something else that's not accounted for, which is the threefold rotational symmetry breaking. When we have one mirror plane, right, we have to break threefold rotational symmetry, and valley polarization doesn't do that. And a possible mechanism for that is proposed recently that it's proposed that when you have these Fermi pocket in one valley, right, exchange interaction could drive an instability where charge carrier, instead of occupying all three pockets at the same time, they want to just condense into one other pocket, right? So the resulting state where all charge carrier occupy one pocket of one valley, break C2, break T, break threefold rotational symmetry naturally, right? And you give rise to this type of phase diagram, meaning that as you keep increasing carrier density, eventually you will come back to something that's threefold symmetric, right? But most importantly, what this also shows is that if threefold rotational symmetry breaking arises from momentum polarization or this spontaneous charge carrier condensation in the momentum space, these pockets are, the orientation of these pockets are locked to the corner of the Brillouin zone, right? So we should have 6 characteristic direction that the mirror plane are locked to, right? So it's something that we can check. So I'm going to show this phenomenon. It's we call it a new type of cascade, right? So it's we're just looking at the mirror axis orientation, and in this case, this is measured from twisted trilayer graphene, right? So we can measure at b equals 0 as a function of band filling, and you see this cascade phenomenon where the mirror plane just jump between these plateaus. The plateaus are separated by 60 degrees. Right, and so mirror plane does seem to be locked to some directions. There's a even more striking phenomenon where we measure both in banal bilayer and twisted trilayer that if you just look at the bottom panel, this is mirror plane direction as a function of b, right? And in this region, this is within presumably one Landau level, or Landau filling of 4 difference. There's a cascade of plateau, and within this one Landau level, there are 6 plateaus, right? Each plateau is separated by 60 degrees. And if we tune magnetic field, essentially we change the Landau level filling across these plateaus. The angular dependence follow this very well-defined rotation where mirror plane just rotate across 2 pi, right? And then you go to the next Landau level, you rinse and repeat. Right. So far, you look like it's consistent with the picture of a valley and momentum polarization. And if it is momentum polarization, right, that means the 6 directions are equivalent, and somehow the exchange interaction spontaneously pick one direction. So, but you should have degenerate ground state. So the next thing we did is to show that look like there is hysteresis or there's tunability, right? For example, at this point, we did a thermal cycle. Before the thermal cycle, the mirror plane is in this direction. And then after a thermal cycle, there's a very clear rotation in the mirror plane, right? Which is consistent with the system just randomly pick one of the degenerate state. At the same time, the mirror plane can also be tuned by current, right? So the top panel is measured before we apply a large current. We do a small current measurement, we get this mirror plane direction, and then we apply a large current and come back, right? And the mirror plane rotates substantially. And this actually gives rise to a hysteresis loop that we actually did the measurement along the current sweep. What we did is that we sweep up and stop here and do an angular dependent measurement, and go all the way up and come back, stop here and do an angular dependent measurement, right? That reveals that there's this hysteresis. Right, okay, so what that shows is that we have rotational symmetry breaking, and rotational symmetry breaking seem to be hysteretic. It's just picking between degenerate ground state, right? And all of these are fairly consistent with valley polarization and momentum polarization, some kind of instability in the momentum space that's giving rise to rotational and transversal symmetry breaking. And since we measured this in banal bilayer graphene, right, that implies valley is polarized. And because in banal bilayer graphene, you apply an electric field that spontaneously break inversion symmetry, that implies the ground state, we should have an anomalous Hall effect, right? Or one of the prediction of the theoretical work is to say, is identifying that anomalous Hall effect is the evidence that will show that you indeed have this momentum polarization. But there's a bit of a history regarding anomalous Hall effect in banal bilayer graphene. People have spent a long time looking for it, and as far as I know, so far, there's no direct evidence of anomalous Hall effect. A lot of these past, I give you 3 references from the last, some are 10 years, more than 10 years ago, some are more recent. But mostly all of these look at the quantum oscillation behavior at finite magnetic field, non-zero magnetic field, and try to infer what happened at b equals 0, right? In my view, that's very indirect. So the clue we have here, or the point I want to make, is that we do have the opportunity for a different type of probe, because we can measure this, let's call it a full angular dependence measurement, right? And we can directly extract a conductivity matrix. And that conductivity matrix does have the off-diagonal term that's Hall conductivity, right? So if we measure this full angular dependence, we should be able to directly see whether or not there is a anomalous Hall conductivity at b equals 0. Okay, and so to just refresh memory, when there's no Hall conductivity, right, the angular dependence look like this. The Hall resistance, the oscillation average to 0, or it's around 0, right? And this RH term should be 0. That's when you have 0 Hall conductivity. And in banal bilayer graphene, what we discover is that there is a special point in the phase space, which is n equals 0 and d equals 0, right? Where the symmetry is actually highest. And at b equals 0, this is what we measure, the angular dependence. And everything is actually perfectly fit using this equation. And the only thing that's outstanding is that RH is non-zero, right? And so this is seemingly indicative of a anomalous Hall conductivity at b equals 0. And if that's the case, then there's a magnetic order that couples to external magnetic field, right? So we can also do this. This is exact same point. And what we did is that we ramped the magnetic field to negative 20 millitesla. It's a very small field and ramp very slowly. And we come back to b equals 0, and you see that this RH term now becomes negative, right? So the behavior, the magnetic hysteresis behavior, and the angular dependence is highly consistent with some kind of anomalous Hall effect. At this point, indeed, if we were to measure the angular dependence of a non-reciprocal response, right, it does show non-reciprocal response. It shows rotational symmetry breaking, this one mirror plane, right? And the fact that we have non-reciprocity means that there could be a momentum polarization in the electronic order, which is connected to the anomalous Hall effect. We can actually go one step further, right? This is just 32 point in 2 channels, and this is a more extensive measurement from many different configuration. The bottom axis, right? Different point comes from different configuration measured at the same density and same displacement field, right? And what we're doing here is that we're fitting it using one conductivity matrix. I was just told actually before this talk that I'm quoting this number wrong. This is plus 2.3. And this is what we're doing here is that we use the principal axis as the mirror plane as a principal axis to define the conductivity matrix. So the off-diagonal term is only contributed by the Hall conductivity, right? So if you do a positive B field training, come back to 0, you get a Hall conductivity of 2.3 E squared over H. And if you do a negative B training, come back to 0, you get a Hall conductivity that's negative 2.1 E squared over H, right? So the Hall conductivity we measure is actually fairly significant, right? Oh, you can see so the first half of the configuration is similar to Hall resistance. You're measuring more or less transverse to the current, right? So you can see that the first half has a very big response, mostly positive, mostly negative, right? And the mean square error of the fit, relative mean square error is roughly 1 to 2%. So the fit quality is pretty high. Okay, all right. And the reason that such a big Hall conductivity give rise to a relatively small Hall resistance, or it's very far away from quantization, is because there is a longitudinal resistance, right? The sample is conductive, but we're just mapping out the direction of its the conductivity matrix. Okay, so I think I'm pretty okay. Maybe I have time to say one thing. Let's come then we come back to the zero field superconducting diode effect, right? The non-reciprocity in the superconducting behavior. The prediction is that if you have superconductivity that arises from a valley imbalanced Fermi surface, then you should see a diode effect. And now what I'm showing is that we do have a way of characterizing what is the valley polarization or the Fermi surface contour in the normal state. So we could make a direct connection, right? So to show that, I plot this phase diagram that's measured in twisted trilayer graphene. in the superconducting phase, right? The superconducting phase diagram has two axes, temperature and current. There's a critical temperature, there's a critical current, right? And at small current but high temperature, the angular dependence look like this. It defines there is a mirror axis in this direction. And if this comes from momentum polarization, right, then C2 and T, or inversion or T, are broken. And at low temperature but large current, we also suppress superconductivity, right? The angular dependence of nonreciprocity look like this. It confirms the same mirror axis rotation, right? But the mirror axis orientation, but the detail of the angular function is slightly different. And in the superconducting phase, we only have longitudinal response, right? We're defining what I'm plotting here is the value of the superconducting diode effect, or the non-reciprocity, the difference between critical current between forward and reverse bias. What's consistent is that it does confirm that rotational symmetry is broken, right? We get a close to one-fold symmetric response. What's interesting is that the mirror plane of the superconducting phase seem to be rotating from the normal state. And I understand in the past, this kind of rotation are argued as evidence for spontaneous symmetry breaking in the superconducting phase. Although in this case, I don't know if I want to push that far, right? But one thing that's clear is that it seemed to be consistent with the interpretation that superconducting diode effect comes from some type of valley and momentum space instability in the normal state. Okay, so let me skip summary but acknowledge the people who contributed to this work, right? Most of the work is done by graduate student, James. He kind of figured out the method to do all the angular fit and expand beyond the angular dependent measurement. Ling is a postdoc who did roughly half of the work, I would say equal contribution, and supported by other graduate students. We benefit from theoretical support from Liang Fu, from MIT, Oscar Vivek. Oscar came up with a method that he convinced me that we can extract way more information compared to just the 32 points, right? So we're actually still working on doing the full angular fit for the non-reciprocal response and try to understand the origin from a microscopic level. We have a collaborator from Colombia and Japan that provided with us the crystal, and the work is supported by NSF, Sloan, and part of that is supported by DoD. Thank you for your attention, and I'll take any question. I'll take question if there's any.
So are there any questions? I guess we'll start with folks that are online here. You can just unmute yourself and start. Go ahead.
Can I go?
Yes, yes,
you hear me?
we can hear you. Yeah.
Hi, John. It's a very nice talk. It has a lot of information. I certainly didn't catch all of it, but I think there are multiple places where you showed it's possible to have spontaneous valley polarization.
Right. Yes.
And you saw some sort of a hysteresis when
Right,
it transitions from one valley state to another valley state, right?
Yes. Yes.
So I'm curious, what pins the valley polarized domain in the sample in order to actually have a hysteresis? Because it's sort of, if I think about magnets, of hysteresis is because something is pinning the domain, right?
Yeah. That's right.
So we're pinning the valley domains here.
Right. I imagine it's the same thing that pins the orbital magnetic order domain, right? Because if it's really just coming from valley polarization, but I should say, you could have valley polarization without having orbital ferromagnetic order.
Yeah, that's the kind of thing which makes me think a little more, because if it's associated with orbital magnetism, you can kind of put it on magnetism, right? But if it's a valley, it's just it's K and K prime in momentum space, right?
Right, that's right, yes.
What actually pins that is like not so clear to me. So I want to hear your thoughts.
Right. So naturally, when you cool down a sample, right, you should have domains of different value forming across the sample. And then another way of asking the question is how do you align the sample to be the same domain to see a big response, right? If you don't have orbital ferromagnetism, because most of the data is taken without orbital ferromagnetism. There's only several points that has orbital ferromagnetism, right? So let me go back to. Right. So in twisted Trotler graphing, right, at d equals 0 or close to d equals 0, twofold rotational symmetry is preserved, or inversion is preserved. And the value polarization breaks C2, break T, but it doesn't break C2T, right? You need something else. You need to break C2T in order to have the magnetic order, in order for value polarization to couple to external magnetic field. And my understanding is that we see orbital ferromagnetism near integer filling because sublattice somehow is spontaneously polarized near these points that give rise to the orbital ferromagnetic order. But away from here, away from this point where we don't see, for the majority of the flat band, we don't see magnetic hysteresis, meaning that there's no orbital ferromagnetic order, but we still see some level of non-reciprocity, right? So those points, I believe, is the scenario where you have value polarization, but you don't have orbital ferromagnetic order. And in fact, the hysteresis I'm showing is taken on the whole doping side, where there's no orbital ferromagnetic order. At least there's no report of that so far in graphene Morley systems. So I guess what that shows is that you could have value polarization without orbital ferromagnetic order. That's one. And two is that value polarization could couple to some other experimental parameter without having to have a magnetic moment, right? So for example, large DC current bias could switch value. There's some kind of coupling there. Or thermal cycle does switch, give you some hysteresis. So the system has some ability of choosing between degenerate state.
So that sounds to me like there's some, it's just basically native, the sample has some inhomogeneous environment that it lives in that would spontaneously choose a value.
Right, yes, right.
The local, is it a strain, or is it whether there's a bubble here, there's not a bubble there, right? Because some of these samples, I probably don't have a whole lot of strain. They're not always twisted, right?
Yeah, so twisted trilayer graphene, there could be much more significant strain level because the Morley superlat is sensitive. Right. And when it's strain does tend to pick one value over the other one, right? But in banal bilayer graphene, I would be surprised if it has a lot of strain, right? And I think that's why in banal bilayer graphene, we see a lot more rotation, like that cascade of let's see. Right, this cascade of rotation in the mirror plane, it's everywhere. And you seem to be rotating a lot more freely. So that means maybe there's not an obvious strain axis, right? And it's a great question you're asking, but it's also a hard one. That without
you might think it shouldn't rotate at all. It should just be one, sort of complete restoration of rotational symmetry.
Right. Yeah, you're right.
You wouldn't be able to pick up any broken axis, right?
Right. I guess there's one somewhat important slide I didn't show that in banal bilayer graphene, if you were to look at the mirror axis orientation as a function of density and displacement field, right? You do have these well-defined regimes where, for example, the blue and red across this transition boundary is a rotation of 180 degree in the polar axis, right? And so that's consistent with the value polarization, right? You have momentum polarization within one valley, and then you switch to momentum polarization in the opposite valley across this boundary. But at the same time, if you look at the angular oscillation, right, it's highly dependent on displacement field. When you open up the band gap, it increased by 3 orders of magnitude, right? So it seemed to be consistent with the fact that it's Coulomb-driven. When you make the band flatter, so the Coulomb is stronger, right? And then this non-reciprocity becomes a lot more robust. But why is it picking one compared to others, that I don't know.
Thanks. It's a very useful discussion. I think it's maybe you need interaction and a little bit of a symmetry breaker somewhere that.
Right, that's right. Yeah. It does seem to be pointing towards spontaneous symmetry breaking, and you need some other external influence to choose one over the other phi. Yeah.
Right.
So are there any other questions? There's not any more online. I'll extend it out here to the room if there's any questions here. If not, I'd like to speak. Oh, okay. Yes, go ahead.
So I'm if I will ask another one if no one else in the room is asking.
Yeah, no, I guess it's you. Go ahead, take it away.
Okay, all right, okay. So yeah, it's really fascinating. So there's the part where you showed the n equals 0, d equals 0, b equals 0.
Right,
and,
yeah.
And I'm gathering you have some evidence pointing to a anomalous Hall effect. Is that what you're trying to say?
Yes.
Okay, so and that so I thought n equals 0 in bilayer graphene, d equals 0 and b equals 0 is an anti-ferromagnet, spin valley coherent anti-ferromagnet, right? So no magnetic moment. But you were telling me that you have enormous Hall effect, like actual spin enormous Hall effect, right? With a magnetic moment.
I think this is a valley. It's an orbital ferromagnet.
Oh, so the enormous Hall here is a valley enormous Hall.
Yes, because it's connected to this non-reciprocity. Spin actually doesn't generate non-reciprocity, right? The non-reciprocity ties the rotational symmetry with the time reversal symmetry breaking. And
okay.
Yeah.
So, okay, I'm glad that got clarified, but I still have a bit of a, because remember this n equals 0 state is the spin valley coherent.
Right.
So both the spin and the valley are actually tied together, right?
Yeah. So
ferromagnet spin and in valley. So you're still breaking that.
Yeah. So that identification, right, comes from the quantum Hall effect regime. You do have to apply either a perpendicular magnetic field or in-plane magnetic field to identify the state that you mentioned.
You in suspended bilayer graphene, you can in fact go down to b equals 0. You don't need any perpendicular, which in which case it becomes a fully in-plane anti-ferromagnet.
Right.
A little bit perpendicular, you go canting a little bit, but in suspended samples, it was actually the state was sort of seen, right?
Right.
So that's the limit you're working at, right?
Yes, but I should point out, or we do see that the anomalous Hall effect we observe pretty much go away and transition to something else at about 50 to 100 millitesla. Right, it's extremely low field transition. And so I am aware of all the identification that people did with a suspended graphene. The dielectric environment is very different, right, between suspended graphene and encapsulated graphene.
That's right.
And it seems like at least at this point, the competition between different potential phases is very sensitive to these environment, or at least that's a possibility. right?
I think it is, which is why I'm excited that because yours is BN sandwiched, right?
Right, BN and graphite sandwiched.
Right, exactly. And in those samples, historically at B equals 0, it hasn't shown anything.
Right.
Interaction is not strong enough.
Yeah, that's right.
So now you're saying there's actually something that's strong enough to show something, but that something does not seem to agree with what the suspended ones are showing. That's what sort of where I try to get a little more understanding of,
Yeah. So there's actually another thing that's more direct, can be more directly compared here. That's what Andrea measured with the Bernal bilayer graphene proximatized to tungsten cyanide, where he shows some indirect evidence that this is some kind of a spin Hall effect, right? Not valley Hall effect. And we actually confirmed that. We did do the same measurement in Bernal bilayer graphene with tungsten cyanide, and this anomalous Hall goes away. But we do have another type of phenomenon that comes out that's not directly associated with non-reciprocity, but that has the same behavior as what Andrea showed, that he interpreted as spin Hall effect, right? So it is an ongoing work that we're working on, and we're hoping that some kind of a spin resonance measurement can shed light onto, can allow us to probe valley and spin at the same time, right? Then we'll be able to pin down exactly which channel is doing what.
Okay, thank you.
Sorry, I just add in June. So now your bilayer graphene is on top of some substrate. It's aligned with substrate or unaligned with substrate?
In the data I'm showing here, it's unaligned. We see no signs of that.
But you mentioned this chain to spin Hall stuff. That is aligned or unaligned?
That's Bernal bilayer graphene putting on a substrate of tungsten cyanide.
Yeah.
Right. So you get proximity induced spin orbit coupling. And
but
as far as
I mean the graphene and the tungsten cyanide, they are aligned or also it's unaligned?
it shouldn't be aligned. But the question, it's a great question, but now we're pushing towards the experimental limit or not experimental limit. Now we're asking the question, how can we tell the difference between aligned and unaligned between Bernal bilayer graphene and tungsten cyanide? Right. So we don't right. So we have indirect evidence, right? We can look at the crystal edge and see how aligned they are. So based on that, it shouldn't be aligned.
I see. Okay, thanks.
Well, if there's no other questions, I'd like to let's thank our speaker one more time.
Thank you guys for the invitation. Hopefully next time I'll visit in person.
Yes, take care.
Bye.